I'm just gonna wait a bit longer for some people to come and then I'll start. Like I'll wait a few minutes. Okay, I'll wait till 3:05 and then I'll start. Okay. I'm gonna start the session. Yep. I'm gonna start. Right now. What is it? Okay. Cool. So let's start. So the first thing in the calculus option is just like simple limit questions, and also like being able to use L'Hopital's rule. So that's like this very basic rule. So just plop open the whiteboard. This is not the thing I wanted to open up. But here. So L'Hopital's rule basically says that if you have if you have the limit as x approaches a, where there's some f of x over some g of x, then this is equal to if f of a and g of a evaluate to 0 or infinity, then so at the same time, then that would result in, then this is the same as saying the limit of x approaches a of f derivative of x and g prime of x. So you differentiate both the top and the bottom. This is the general definition for the limit, which is like pretty like simple that you can like try and solve for. So a quick example is looking at this document right over here. So if you notice, so just this question here, using this rule, and you have a sequence un. So we need to find the we need to show that the sequence converges, where the sequence is given by 3n plus 2 over 2n minus 1. So these are functions of n. So what ends up happening is that you want to find the limit as n approaches infinity of un. So that's the same as saying the limit as n approaches infinity of 3n plus 2 over 2n minus 1, which you can differentiate the top and the bottom. So that's the same as saying the limit as n approaches infinity. Well, first of all, we need to note that when you try and plug in infinity for 3n plus 2, you get an infinity in the top, and if you try and plug in infinity for 2n minus 1, you get a positive infinity in the bottom as well. So you get an infinity over infinity, which indicates that it's in an indeterminate form, which basically satisfies this condition over here. And since it's an indeterminate form, you can proceed with L'Hopital's rule, and you can go ahead and try and do differentiate the top and the bottom. And you'll get 3, because the derivative of 3n plus 2 with respect to n is 3. And the same for the bottom, which is 3 over 2. So the limit is n approaches infinity of 3 over 2. There's no n's in here anymore. It's just equal to 3 over 2. So the limit is of L, value of L is equal to 3 over 2. Okay. Then there's a couple more sequences over here, which can also be shown to diverge. 1 second. Wait. I can give you guys some time to try and wait. This is the wrong. Oh my god. Why is this doing this? What the hell? No, this is what the fuck is happening? I can't seem to. This is confusing. I don't get this. That's not what I was pasting. Okay, one second. I'm gonna try and work over here. It works here, but it doesn't work on my whiteboard. Okay, just guys, you can try and solve this problem, and I'll give you like 5 minutes, and let's see if anyone can solve these, because they're the simple limits. So I'll leave it until 3:15 to try and solve for these. And if anyone has any like specific problems with either one of them, I'll do the question then as well. Oh yeah, sure. I can do the full key. That's fine. So these questions, you don't actually need to do much like extra manipulation for each one. You should be able to use the answer from the previous part, which is that the limit of un is 3/2, to be able to solve for these ones as well. And to show that they're not. Yeah. Oh, the full question. Oh, I think now this makes a whole lot more sense. Here's the question. And I'm only looking at part A to part C, so that's it. So don't have to look at B or D. That's fine. Okay, I'll go ahead and show how to solve each problem. This is quite simple, so let's go ahead. No, this is, I'm still so confused. This is just, what if I copy this image and paste it in here? Nope, it's still pasting in the wrong thing. I'm so utterly confused, like, why is this happening? Paste, I don't want to paste this anymore. I literally just paste that and it works, but then if I paste that, it doesn't work. This is, yeah, I am using a snippet tool. This is like, plop, okay, wait. What if I reload it and open it up again? Get rid of that. Oh, there we go. Probably just reload. Here we go, so let's quickly solve each of these. There's two ways that you could go about this. The super simple way is, this is not straight. Lock into place maybe? Nope. Anyways, so the two ways you could solve for the first one, so un over n, so un over n. One way you could do it is you could literally just put like 3n plus 2 over 2n minus 1 over n and then like do everything all over again. But there's a slightly, like you could like try and simplify and then like make it into like a fraction again and then like use L'Hopital's rule again. But there's a quicker way, which is in noticing that un over n is equal to un times 1 over n. So you're trying to check for the limit as n approaches infinity of un times 1 over n. And note that un we know is the limit is 3 over 2, but 1 over n is 0, so that's 3 over 2 times 0. So we know that overall the limit as n approaches infinity for un over n is going to be equal to 0, and this does converge hence. Now for the second one, again we could do all of the L'Hopital's rule stuff again. You can plug it in, then do all of the manipulation to get back to the same situation. But then that's not worth the time for like how many marks this is worth. So 1 over 2 un minus 2. Again, use the limit definition. So you know that you need to find limit as n approaches infinity of 2 times un minus 2. So this is what you need to figure out, and that's equal to the limit as n approaches infinity of 1 over 2 times 3 over 2 minus 2, like so, which is again equal to the limit as n approaches infinity, which is, I mean, you don't need the limit anymore once you've substituted what un is equal to. So that's equal to 1 over 3 minus 2, since the 2 and the 2 cancel. It's 1 over 3 minus 2, which is equal to 1. Again, it converges. So the second limit also converges. The final limit, one would think that this converges. However, it doesn't converge because negative 1 to the power of n means that it keeps flipping from negative to positive. So what ends up happening is that you have 3 over 2 is obviously the limit it's approaching for un, but because you have the negative 1 over n in the front, it goes from negative to positive, and then negative again, and then positive again, negative and positive, negative and positive. So it never actually converges to any given point. It just keeps hopping up and down, and hence that's why we say it doesn't converge. So yeah, that's that question. Okay, that's basically what that is. Okay, so now I'll just go, just quickly give a definition on continuity and differentiability. So in order for a function to be, so in the core option you learn that in order for a function to be continuous, you need to make sure that the function basically has like the same values at that point. So like if you have a function like so, the only condition that's actually required is like that. So like to make sure that there's no hop or skip, or like it doesn't start over here and then like it doesn't have to like hop from there all the way down to here or anything like that. So basically you only need to like have continuity, which means that like there's no point where it has to jump and there's always like a consistent value across the domain. However, for the calc option, it's also important that you have continuity and differentiability. So that means that at any given point, you need to make sure that the derivative is the same at both points, and that the value is also the same at 2 points. So for example, if we had a function f of x, which is equal to h of x from negative infinity to a, and g of x from a to positive infinity. Given these conditions, what you want to make sure is that you have continuity and differentiability. So you want to make sure that h of a is equal to g of a. This would be a satisfying condition for the core option, for the core material, but you also need to know that there's continuity and differentiability. So hence you would also need to make sure that you have the derivative of the h prime of a is also equal to g prime of a, and you have these two conditions to meet. So usually what the IB does is that they set up like a simultaneous equation kind of thing. So they'll have like they'll have a h of x over here with like some variables inside of what the function looks like, and the g of x with some variable like inside of the function and what it looks like. and you'll have some a maybe or something like that. And essentially, what they'll make you do is they'll actually make you find find these two equations. So like state this equation, then state this equation, and then simultaneously solve for whatever variables they're giving you, and usually it'll work out. So this is like two pieces of information that you have from any given function, piecewise defined function like this, and you need to use these two definitions in order to actually solve for any simultaneous equations that they might pop up at you. So yeah, that's how you would do this. So yeah, that's what you need to make. Remember continuity and differentiability. Just remember these two definitions and you'll be good. Sometimes they'll have like 3 different functions, then you have to like use several different like simultaneous equations. It'll like get more complicated, but like essentially it's the same idea. So yeah. Pop over. So now for infinite series. So I did just give an example where you're looking at like the convergence of a sequence. So so just looking at un and what like the behavior of something like un. However, it is more useful to also look at the behavior of any given un from n equals to 1 to infinity. So like checking how the value changes for an infinite sum. So if you're going to sum every single term of them, how does that value change? And there's a few different tests you can use to check whether or not it converges in this sense. And I'm just going to go through each one that you need to know. So the first one is the direct comparison test. So the direct comparison test says, so basically what we're doing here is we're checking that for any given like an, which is some sequence, so like some sequence, if you sum this sequence until infinity, what is the value going to be? Is it going to be a convergent value or not? I mean, straight off the bat, you know that if it's increasing, then it's not going to converge. So like it needs to be decreasing. It can't even be like monotonous. It can't be the same value. Like if you just have 1, if it's just always 1, and you keep adding 1 to infinity, you're not going to get a convergent number. So it needs to be decreasing. That's for 1. But you don't know for sure if it's decreasing fast enough, because some sequences might be decreasing, but they're decreasing so slowly that they never actually converge to any value. So that's what we're doing over here is we're just checking for different values. So for example, so the first is a direct comparison test. So you have a to the an, say we have an, and we're going to check if it converges. If you can find some given bn which does converge, so if we find a bn which we know to converge, and an is less than bn, then we know that an also converges. Okay, now to write this in better notation, the limit of an, the sum from n equals to 1 to infinity of an converges if an, just one of the parts of the sequence is less than bn, and bn and the sum of bn to infinity n equals to 1 converges. So if these two conditions are satisfied, then this one also converges. Now this makes sense, obviously. So if you have some larger sequence than an that does converge, then you know for a fact that the sum of an must also converge. So for example, if you had something like 1 over, like, so if say that bn, say that you have an and you want an to be, let's say 1 over n cubed. No, that's not a good example. If you had an be 1 over n squared plus 1, right? What if you wanted to check if this converges and you don't know for sure? One way you could check is that you could look at bn, which is equal to 1 over n squared, and you know that 1 over n squared plus 1 is less than 1 over n squared for all positive values of n, because when you have a plus 1 in the denominator, it's going to be slightly smaller than the 1 over n squared. And since you know that 1 over n squared definitely does converge, then you can make sure to say that this one also converges, since it's smaller than that one. However, you need to make sure to know that if bn diverges, that does not say that an diverges, because you could just find some arbitrary sequence that's like way larger than an, which diverges, but an will not diverge. So you need to make sure that it satisfies these conditions, because the contrapositive is not true. So if an converges, for example, that doesn't necessarily say that Bn converges. So if 1 over n squared plus 1 converges and it's smaller than 1 over n squared, that doesn't necessarily mean that 1 over n squared converges. So you need to make sure you're thinking carefully about what like direction you're doing these. So like are you what implications are you making? So the implication goes the other way around. You need to make sure that Bn converges and An is less than Bn, and only under that case can An converge. If you try and do it the opposite way around, you'll mess it up, and then it just won't be logically consistent. And the best way to make sure you don't mess it up is to think about what it means when you're saying what this test really means. And what it means is that if you have some number that's bigger and it is converging, then any smaller number than that will converge as well. But you cannot work it the other way around. So that's what you need to be sure of. And this comes into definitely into play when you're looking at the second test that we're going to look at, which is, let's go check. Okay, cool. I think the second test we're going to look at, which is the okay. If you guys have any questions, you can either like turn on your mic in the VC and just ask a question, or you can pop it in over here and ping me, and I'll make sure to try and look in. Okay, so the limit comparison test is the next one, which is trying to figure out, trying to compare to another comparison sequence, which also seems to work. So if you have, so this is the definition. So the limit as n approaches infinity. Say you have some sequence an over some sequence bn, which is equal to c. So that's some limit c, and so what this says is that if Bn converges, then An converges, and if Bn diverges, then An also diverges. And this is given that C is a finite positive number. So given that C is a finite positive number, if Bn converges, then An converges. And if Bn diverges, then An also diverges. So the key thing about this in noticing that the biggest mistake that might come up is that you end up like flipping this around. So you need to know that the denominator implies the numerator. So if Bn converges, then An converges. And if Bn diverges, then An diverges. You cannot do it the other way around. So if you use this definition and say, for example, you mess up and you flip up the denominator and the numerator, you will mess this up. So for example, they give you some equations, they give you some function and some sequence, and they say that say it's an, right? They say it's an, and you know it diverges. And if you put it in the numerator and you're trying to test if some other function converges or diverges, and you put that in the denominator, this will not work. So you need to make sure that you're analyzing this with respect to the denominator. So the denominator is at the bottom, and the denominator has to be the known value, and that's how the limit comparison test works. So you need to be sure of that you don't flip this up and mix it around, and then this will all like work out correctly. So if Bn converges, An converges, and if Bn diverges, An will also diverge. And you need to make sure that the known value is Bn at the bottom over here. Okay. Yeah. So if you have so it's very possible that you're like, oh well. I mean that comes back to something like, so the proof of this is quite difficult, and like it's not very easy to like prove this. It probably like requires some kind of set theory. But basically, this is the same principle as something in the L'Hopital's rule. So in the L'Hopital's rule, we looked at like some functions that the numerator diverges to infinity, and the denominator also diverges to infinity. However, at the end, they both diverge to a positive value. So for example, if we were looking at just the question right before, so if we're looking at limit as n approaches infinity of like 3n minus 1 over 2n plus 2, right? This diverges to infinity. This also diverges to infinity. Essentially, if you set these, if you use L'Hopital's rule, this will end up being 3 over 2, which is what we showed before. So it does converge to a finite positive value, even if the bottom and the top aren't necessarily either one of them is not convergent. So if you have two things that are going to infinity, the fact that they're both going to some infinity will show that like they're they might just converge. So not like you, but sometimes the numerator is growing at like a faster infinity than the denominator, and then in that case you're gonna have like a way faster like infinity. But um, you need to show that basically. So you need to like just use it you need to like show how everything is working out properly. You can't just like guess like, and that's basically it. Like, but it's very possible that you have a quotient of divergent values that ends up with a finite value, as we just showed like the L'Hopital's rule or whatever. So yeah, that's that. I think Aryan's typing something. I see that's probably important, so I'll just wait for him to finish, I guess. There's nothing? Okay. What do you mean prove it for infinity over infinity indeterminate value? So like if the top and bottom are going to infinity, then you can just um, you can just use L'Hopital's rule, and the same for 0 over 0. Um, Not necessarily. I don't know the proof for either of L'Hopital's rules. Like, I don't know the proof for why either of them like why like works at all. Um, and I don't think the actual proof for L'Hopital's rule is pertinent to the syllabus, anyways. I mean, I could probably go and find out, but it's not very relevant to the actual IB syllabus. But like right off the top of my head, I do not like remember the proof for L'Hopital's. Okay, I'm just waiting for like SM to type and then see if there's anything. Well, yeah, that's true, but specifically saying why their like derivatives represent like limits, that's I don't know the rigorous proof for it. No, it's after like after the session I can like after I'm done with all the content I can probably like search it up and explain it here. Anyways, it's fine. Like, but I just want to get along with the content right now. So yeah, I'll just continue for now. So the next test is the ratio test. Basically, what the ratio test says is that another way you can check for if some sequence converges is by checking the value right above it. So so here it is. So if you want to check the sum of a function from n equals to 1 to infinity of an, one way that you do this is you can check the limit as n approaches infinity of an plus 1 over an. And essentially what that means is that if this will give you some value, some number. So remember you need to check, you take the absolute value of this. And this will give you some limit. And if this limit is less than 1, then you're going to end up with a convergent series. So so this is going to give you some limit L, and if L is less than 1, then an converges, and if L is greater than 1, it diverges, and if L is equal to 1, it was inconclusive, which means that if it was equal to 1, the test failed, and the test didn't actually end up with anything, and there's no result. It's just there's no actual result from the test done. So if it's less than 1, you can converge. If it's more than 1, it diverges. But if it's equal to 1, it's inconclusive. So quickly, just to try this out, you guys can. Oh, you have a proof of L'Hopital's. Okay, that's fine. Just try n over 5 to the power of n. That's like a pretty simple example to try for this. So just wait. We have a Tekkit bot here, right? So I'll just do this. So try and find. So just try and solve, do this for this question, and it'll just and I'll just give you 2 minutes maybe. That's fine. Okay, so I'll just go over it right now. N over 5 to the power of n. I mean, this is a super simple example. So what I would do is that I need to check for n over 5 to the n. So that's n plus 1 over 5 to the power of n plus 1 over n over 5 to the n. And I need to check the limit as n approaches infinity for this and the absolute values, but I know everything's going to be positive, so it doesn't matter what the absolute values for now, what it is. Sometimes it could matter. Then I can simplify, and I notice that the 5 to the n over here cancels with the 5 to the n over here, and just leaves a 5 over there. And then if I just look at what happens to the fraction, it just becomes n plus 1 over 5n. So the limit is n approaches infinity of n plus 1 over 5n. Notice that this is an indeterminate form, so if you plug in infinity for the top numerator, we get infinity, and for the denominator, we also get infinity. So it ends up being, this is infinity over infinity. So we can use the L'Hopital's rule and differentiate both the top and the bottom. So the limit as n approaches infinity. If you differentiate the top, if it's n plus 1, you get 1. And you differentiate the bottom, you get 5. So the limit as n approaches infinity is 1 over 5. So that's what the answer for this. So we know that now, because it's 1 over 5 and that's less than 1, that means that indeed n over 5 to the n converges by the ratio test. So that's probably the question. Yep. So yeah, converging. The next one is the integral test. So this one's a slightly simpler test, really. It's this one is very intuitive. It's this one makes sense. So essentially, what that if you're ever looking at a function, right? So whenever you're looking at a sequence, right? Say for example, you're looking at something like x squared. Just for simplicity, I'm gonna try x squared, and it looks something like this. And you're trying to sum x squared values from. So you're trying to sum from x equals to 1 to infinity of x squared values, right? So what does this actually mean? So let's look at for x equals to 1 what that means. For x equals to 1, so for x equals to 1, right? Okay, this is kind of a skewed scaling, but that's okay. So for x equals to 1, you're gonna get 1. So let's just say this is 1. You're gonna get 1. So like let's think about this in terms of areas, right? So like, what that means is that for x equals to 1, you're gonna get like for x squared you're gonna get some value of 1, and you're gonna like assign it. It's gonna be like an area of a rectangle of this width, right? And if you're gonna have 2, you're gonna end up with 4. So you're gonna have a height of 4. And that's gonna be your height of 4. And again, it's gonna be like if the total area that you're summing up to add that is gonna be this. So essentially, what you're doing is you're creating like these Riemann sums. So it's like these it's basically like you're integrating, but you're taking like the upper integral. So like you're adding up these rectangles that are slightly large at these values, and that's essentially what it means to take a sum of something. And this leads up to something else really interesting called discrete calculus, but that's okay, we don't have to talk about that right now. And essentially like that's what 9 is, and again that's another block. So if you add up all these blocks, you'll get the area of whatever this sum is, right? Now, knowing that these are all these blocks that you're adding up, a really interesting property should be that if you can think about this sum essentially as these areas being summed up as little blocks, then couldn't you also just think of this sum as the integral? So this is some variant of the integral. And one way that you can think about this is you can think about it like, you can think about it in saying that what if we just took the integral of this function? So if we just integrated to some value x, so we just integrated x squared from 1 to infinity, and we checked what the value of this is instead, and knowing that if we check what the area under this curve is, that will be able to give us what the area of all of these blocks added up together, at least approximately, because that's what integration kind of is doing anyways. So if this area converges, then we know that these blocks will also converge. And if the area diverges, we know these blocks diverge, because these blocks approximate the value of this function. And if this function if this function's value, the integral value converges, then the block's value must converge. And if this function's value diverges, if their integral's value diverges, then we know that these blocks must also diverge, and hence this also diverges. So for example, if you were like look at x squared, obviously you know if we integrate x squared, that's going to give us 1/3 x cubed. And if you're evaluating that from 1 to infinity, you'll notice that infinity plugged into 1/3 x cubed is infinity. So you know that this integral's value is basically infinity. So it diverges essentially. So this integral's value diverges, and hence we know that the sum of all x squareds will also diverge. And we already knew that. We knew that if you kept adding up x squareds, it's going to diverge into some infinite value. So this is the use of the integral test, which is super cool. And the integral test basically says that if the integral diverges, then the actual function, the actual sequence will also diverge, when the series will diverge. And if the integral converges, then the series will also converge. And that's the integral test. Next test, which is again, you just need to integrate. So basically, you just need to be able to integrate. And if you're able to integrate, you'll be able to do this. So yeah, if all the integral tests might be sometimes really difficult though, because like it's an integral, and like integrals are difficult to like solve. So that's why it's like not necessarily your first choice. Like your first choice should be direct comparison, limit comparison, or ratio test. I always go for ratio test first, because like ratio test is like surefire method to work. Like limit and direct, you need to like search for some other function to find, which is difficult. But the next super easy one is the p series test, which is 1 over n to the p. So if you have any function which is 1 over n to the p, or anything like analogous to this, like 1 over n plus p plus c, so like some constant or something like that, you know that depending on the value of p, this is going to converge or diverge. So if p is greater than 1, specifically greater than 1, then this diverges. But if p is less than or equal to 1, then this diverges. So if p is greater than 1, this series will converge. And if p is less than or equal to 1, this series will diverge. So note that this means that the sum of 1 over n, from n equals to 1 to infinity, this diverges. This diverges because it's 1 over n to the power of 1. However, we know that 1 over n squared converges since p is equal to 2. and that's greater than 1. So this is the P-series test. So this is a very, very simple test, and it's not really a test even. It's just a fact that like should like be ingrained in your head. And essentially, with this fact, you can use like functions like these to compare to in the direct comparison test or the limit comparison test, and it's very useful. So that's that. Then the next one is conditional convergence. So oftentimes there'll be series which look like this. So oftentimes you'll end up with series which look like the sum as from n equal to 1 to infinity of negative 1 to the power of n an. So what this basically means is that you have an jumping up and down, becoming negative, positive, negative, positive, negative, positive, and if you keep adding all of these up, when is it going to converge? When is it not going to converge? So this is something called the alternating series, which means basically like it's alternating from negative to positive. So you can use something called the alternating series test if you ever see this, and the alternating series test is a very satisfying test. It's a beautiful test in that as long as an is decreasing, as long as an is decreasing, this implies that this sum is convergent. So all you need for this series to be convergent is that an is decreasing. So even if you had like 1 over n, which normally would diverge if you just kept adding them, as long as it's decreasing, it will converge if it's an alternating series. So if it keeps popping up and down, it will converge. So what you would say for this is that it's conditionally convergent. You would say that this sequence is convergent only under the condition that it's an alternating series. So it's conditionally convergent. However, whenever you use like the ratio test, the P-series test, all the other different kinds of tests, you know that those functions are absolutely convergent, which means that if we took the absolute value of them, so if I took the absolute value of this, then it's still going to give me the exact same function. And yeah, that's basically how that works. If you took the absolute value of them, which means when you take the absolute value, the negative 1 to the power of n cancels out because it doesn't mean anything anymore. And if it converges then, using the other tests, then it's absolutely convergent. However, if it has negative 1 to the power of n's in it, like that, then you can use the alternating series test and you'll know that if an is decreasing, then it is definitely convergent. That's conditional convergence. Okay, so the next thing is so sometimes what's it? Check this out. Sometimes in your series you'll have x's, for example. So your series could have this could be, look at this. Assume there's some series where you have some x times some an, and essentially what you want to check for is for what values of x. So for what values of x? Well, for what values of x is xan convergent, right? So the way that you would naturally do this is by using the ratio test normally. So let's just pop over and look. So when you say for what values of x, you're looking at for two things. So one, you're looking for an interval. So you're looking for what interval is this going to converge for, and then they might also ask you for what the radius of that interval is. So basically, what the radius is basically half of the length of that interval. So if you're like looking at one midpoint where that interval stops, like the midpoint of that interval, like what is the distance to both ends of that interval? So again, that's what like the radius means, and I'll explain that once I get look at the example. So if you guys would like to go ahead and try this example, like just for like the sake of like understanding how this works, I'm just gonna like consider the power series and the radius is converged by the radius. So just try this part for now, and I'll pop it in over here, and just take like 5 minutes to try this. okay, I'll go ahead and solve it. If no one has any, like, if anyone has any, like, concerns, yeah, ask me, but I'm gonna go ahead and solve this. So, this is the power series, find the radius find the radius of convergence, and find the interval of convergence. So, what is this stuff? Okay, whatever. It's fine. Consider power series. So let's look at what this function really is. So it's some uk, which is equal to k, x to the k, over 2 to the k. And that's what this sequence is. However, we need to check for what values of x does this actually converge. So the best way to look for that is to use the ratio test, which is what I said before. So check the limit as k approaches infinity. So I'm gonna replace everything with k's with n's. So I don't know, I'll keep saying n, and I just want to make sure I say n instead. So the limit as n approaches infinity of so u n plus 1, so that's k plus 1 times x to the power of k plus 1 over 2 to the k plus 1 over just what this. No, I should have put n's. I'm very stupid. Okay. N x to the n plus 1. Oh, I'm n plus 1 over 2n plus 1 over n x to the n over 2 to the n. There we go. So quick, let's do some simplification. So the 2n cancels out over here, 2n cancels over there, leaves just a 2 over there. Then the x to the n over here cancels out with the x to the n over here, just leaving an x up there. Note that I forgot to put in the absolute value signs. So there's absolute values of both the top and the bottom. So I did all the cancellations over there. After I finish all of that, I plop it over. I get the limit as n approaches infinity is equal to the limit as n approaches infinity of n plus 1 times x over 2n. Okay, so again, this, so again, I have absolute value signs over the entire thing. And notice there's another problem over here. We have another indeterminate form. So if as n approaches infinity, n plus 1 is going to approach infinity, and 2n is also going to approach infinity. So this overall, both of them go towards infinity. So again, L'Hopital's rule time. And again, note how we use L'Hopital's rule while we're using ratio test, like the ratio test. It's fine. It always works out. Just make sure you're doing it in the correct scenario, the correct context. So if you differentiate the top, that's xn plus x. Well, really it's x times n plus 1. So it's just if you differentiate this, you're gonna get xn plus x, which when you differentiate that, it's just x. It's gonna be left up with x. And 2n, when you differentiate that, it's gonna end up with 2. So the limit as n approaches infinity is the absolute value of x over 2. And note that now that you have no more n's, it doesn't matter, you don't have to have the limit anymore. So this is equal to the absolute value of x over 2. Note that in order for this to converge, you need to make sure that it's less than 1. So your condition is that the absolute value of x over 2 is less than 1. And note that this is the condition that x over 2 is less than 1, but also greater than negative 1. So it's within that range. And essentially this is what it means by having like that kind of like like this ratio, like this like this radius around the interval. So like you're inside negative 1 and 1. Now note, if you just multiply everything by 2, you'll get the x needs to be between 2 and negative 2. So your radius is equal to 2, and your interval is equal to negative 2, 2, like that. So it's just between negative 2 and 2. So again, so what you're basically doing is you're like looking at a number line, and you're looking at the value of 0, you're looking at the value of negative 2, you're looking at the value of 2, and you're just checking in between these values, what is the radius essentially. So like what is this like length here? Well, that's the radius, and then this is your interval. Now note that we're not done with what we had to do yet. We're not necessarily finished with the actual question, which is that note that over here how we just use the not our limits over here. So we just said that x is greater than negative 2 and less than 2. However, we need to check for whether or not they're also convergent at 2 and -2. So what you need to do is you need to go back to the original function, which is kx to the power of k, 2 to the k. You need to check for -2 and also check for 2. So if we're going to look at uk, you need to check for -2 to make sure that it converges there or not. It could not converge there, it's okay. So basically what you have to do is you need to check. So first let's check for 2 to the power, for 2. So when x is equal to 2, you get k times 2 to the k over 2 to the k. Now the 2 to the k over here cancels with the 2 to the k over here. And that just means that you have k, just k. And if you have just k, and you keep adding up k's, and they're all the same k, you're gonna end up diverging. So you now know that you were correct in saying that it's less than 2. Because if it is 2, it doesn't work anymore. Does not work anymore. So now we check for -2, and if you can predict, this will probably be a similar result. If you have -2, it's going to be k -2 to the power of k over 2 to the k, which is equal to k times -1 to the power of k times 2 to the k over 2 to the k. And now the 2 to the k over here cancel with 2 to the k over here. You're left with k times -1 to the power of k. Note how we said earlier that now this is an alternating series. It keeps popping up from positive to negative. However, the issue is that the alternating series test requires that whatever the negative and positive thing that's becoming is decreasing. However, k is always increasing. So as k keeps increasing or k stays the same, it just keeps popping up and down, and the series will never actually converge. So yeah, that's a problem. So yeah, that's how that one works. I'm so sorry for preponing it an hour. I'm an idiot. It's fine. It's not fine. It's okay. It's not okay. So yeah, and that's basically what the solution says as well. That's just that was literally just that's several marks. That's a lot of marks. Yeah. See, you get a lot of marks. Okay, you get a lot of marks for this stuff. Just showing all that stuff, that was like 10 marks. And if you know your stuff, because like the actual numerical calculations are very minimal, so it's very fun. That's a fun question. You get a lot of bang for your buck, you know. I don't know why I'm saying this stuff. It's fine. So here, let's look at the final thing. A few different things now. So okay, yeah, we have a bunch more stuff. I'm gonna go drink some water. I'll be back in a little while. 1 second. I'll be back in like 5 minutes. Okay, I'm back. Okay, next part of the content. So I'm just get finish off with this integral stuff. It's boring. Differential equations are the real shit. Wait, let's see. Rolls theorem, series, Turner series. Okay, I'll do differential equations last. I'll do the integrals first now. Yeah, so I plopped those in. I have that covered as well. No worries. I always find that the whole integrals, like the upper bound, lower bound, the rectangle stuff, there isn't much to teach. It's just like example based. So really like knowing that when you're evaluating an integral, but essentially, I went over this just like a little earlier when I was looking at the Riemann sums. So this is something called the Riemann sums. So when we do integration, we're actually doing a specific form of integration called Riemann integration, which is basically like you looking at these rectangles and the value of rectangles as they like approach some infinitesimal value. And Riemann integration is this is Riemann integration basically. And Riemann integration uses rectangles, right? So what you're looking at is these little blocks like this of some length, and essentially this is called the upper bound integral. So these are these upper bound like sums of little blocks, right? And this is the upper bound because these actually combine the area of the area underneath this curve with these little extra chunks over here, right? So this is an upper bound integral. However, you also have lower bound integrals. So for example, you could also have lower bounds. So lower bound ones actually look a little different. So they look like this. It's actually hard to draw them actually. Here, it's like that, and like that, and like that. And these are called lower bound integrals for Riemann, specifically because they have some area of the actual integral, but they're missing this portion right over here. So that's a lower bound for whatever like integral you're looking at, and essentially you should just be able to like notice what's happening. Like this is how integration is like developed basically by looking at these like infinitesimal like small rectangles. However, they often ask you questions about the upper bound, the lower bound, these like big rectangles, small rectangles, and basically how these look. So you should be able to look at their areas and understand what these areas mean. Specifically in that they all have width of 1, that's for sure, always. And depending on whether or not they're the upper bound or the lower bound, they have a different y value. So, for example, I'm just going to look at one really quick example. So I'm just going to erase all of this again. Just to give you an idea of what I mean by comparing the upper bound and the lower bound at the same values. So, if you have some value x squared, right? You have some curve that this is x squared, right? You could have actually, I'm going to use different colors for this because I think that'll be very useful. Okay, let's just try different colors. I'm going to try blue. I could have this as my lower bound, right? So that's my lower bound rectangle. And I can also have an upper bound rectangle. So that's if I go all the way up here, then go there, and then come back down, right? That's my upper bound rectangle. Now, knowing that this curve is x squared, what do each of these represent? And now we can like look at what these represent. So let's say that this is some value x, and this is some value x plus 1. And this height over here, so this height over here is what it is evaluated at x. This height over here is x squared, and this height over here is x plus 1 squared, x plus 1 whole squared. So knowing this whole height, this is height x plus 1 squared because that's what this curve represented at x plus 1. So evaluated at x plus 1. That's x plus 1 squared, this is x squared. So if you look at what each of these like rectangles mean, so that means that the red rectangle area is equal to x plus 1 squared, that's the height, and the width is 1. So the area of the red rectangle is x plus 1 squared, and the area of the blue rectangle, so actually let's flip colors for that. area for the blue rectangle is equal to x squared. So sometimes what they'll do in questions is that they'll like give you like some x plus 1 inside a function, and then they'll give you some like x inside a function, and then they'll ask you like what does the x plus 1 represent, or what does the x represent. And basically when you're looking at what the x plus 1 represents, it's actually at the exact same spot where the x is, like for the lower bound integral, that's where the x plus 1 is for the upper bound integral. And this is just like basically this is like half like trivia of like Riemann integration and how this looks like. But sometimes just knowing like this is what it looks like can help in a question. And I saw like a question like this in the May 2019 papers, and yeah, this is what that looks like basically. So yeah, and now looking at one of the examples, one of these examples actually uses directly noticing that you have upper bound integrals and you have lower bound integrals. And so let's just look at what that looks like. Yeah, okay, cool. Doesn't do much. So let's look at one of these questions. So find the value. So this is gonna give you like 5 minutes to think about what this means and like try and solve this. And yeah, so just go ahead. So I strongly recommend drawing a graph out or something like that to try and understand what this means. It would help a lot more with trying to understand this. Yeah, so go ahead. Oh, it looks hard. It really isn't. Draw it out. You'll see what I mean. Like why I was like showing you the upper bound and the lower bound thing. It'll like make sense. Okay, cool. Are you guys good? Like, did you guys try the question? I'm gonna solve it right now. Nope. My whiteboard is popping itself over again. Oh God, I hate Microsoft. Why doesn't it like auto lock itself? That's like so annoying. I can't tell if it's like 90 degrees all the time. So find the value of the integral for to infinity of 1 over x squared. I'm not gonna sit and solve the integral. It's a very simple integral. The value of that integral is just equal to. Oh, I should probably change the color back to normal. It's just 1 over 32, and I think that's what the answer says as well. So if you just quickly use this here, there, yeah, it's 1 over 32. So that's correct. Look back. So illustrate graphically the inequality over here. So let's first look at what this actually like looks like, what the center function looks like, right? So let's look at what that looks like. I'm just going to use black to note the center function. So 1 over x cubed. 1 over x cubed is like a rapidly decreasing function. So basically, as x to infinity, it just decreases like so. So that's what I'm going to make it look like. And I'm going to assume that 4 is like somewhere over here. So I'm just going to draw a. Fine. So what this represents is that this area over here. So wait, let me use a highlighter for that. That's like pretty good, right? So this area over here is. Oh wait, can I like highlight it entirely? Can I fill in this? Does it fill? Nope, it doesn't fill. So this area is your area for what this integral is. So this is from 4 to infinity, 1 over x cubed dx. This is 1 over 32. That's what that area is. However, you want to check what does this mean, and what does this mean, but graphically. So let's think about this carefully. So 1 over n cubed, right? From n equals to 5 all the way to infinity. So let's just pop over to n equals to 5 for a second, right? So let's look at. I'm gonna denote everything with this. Everything related to this function is going to be in red, and everything related to the other function is going to be in blue. So this one is. Let's just pop over to 5 and see what happens. So you pop over to 5. What's the value of 1 over n cubed at 5? That's 1 over 25. So that's like. So let's just pop it up. Let's just go all the way up, right? Just slowly go up till here, right? And basically what you want to try and do is that you want to try and represent that value as a rectangle. So you know that the value of 1 over n cubed when n is equal to 5 is 1 over 25. So you want to make sure that you have some like rectangle with height 1 over 25. 1 over 25, 1 over 125. And you want to and you just want to show what that looks like with width 1, because if you have width 1 and height of 1 over 25, then you're going to end up with a rectangle that shows that sum perfectly. So what you do is you just what do you think about this for a quick other second? This is like making my brain go a little poop. Wait a second. Yeah, okay, this makes sense. So we just do that, like so. So we do that, and this rectangle represents a value when n equals to 5. Now if you look at n equals to 6, right? If you look at 6, we're going to end up popping up all the way to here. This is our value. We make a width of 1, and this is our value of this sum. So now we know that this inequality, graphically speaking, this like function over here, graphically speaking, looks like this. We're going to be going up till here, checking with 1, and then using this, right? And so you can just show these rectangles and what they look like, and indicate that this is actually equal to 1 over n cubed. And then let's look at what the other one looks like. So at n equals to 4, so what this one actually is doing, so it looks at n equals to 4, and it goes all the way up to that value, then creates a height of 1. And what that looks like is this. It looks like that. And this entire area is the blue one. And similarly for n equals to 5, it starts over here and creates one out over here. And that's this area right over here. And if you were to look at the same, it looks over here, it's the exact same over here. Essentially what's being done over here is that this this is the upper bound. And this is the lower bound. And you know this is the lower bound and this is the upper bound, since first of all, you can literally see it in the inequality. This is an upper bound for the function, this is the lower bound for the function. However, you can see it more graphically speaking, in saying that when you're taking when you're looking at like Riemann integration and you're looking at these blocks being added up, the red blocks are the lower bound blocks, which means that these are slightly smaller than the actual area. And the blue blocks are the upper bound blocks because they're slightly larger than the actual area. So if you were to evaluate what this upper bound is and what this lower bound is, you could find bounds for what this value is, and that's very useful. So that's basically what this means, like illustrated graphically. So you need to show at least 3 triangles of each one of them to show like that there's a difference over here, and that this one represents the upper bound, this one represents the lower bound. And I see that's what this is about. That's what this is doing. And yeah, I have a lot of things. Oh, that's not from here. Okay, cool. Now looking at the next 2 parts of the question, these are a little more intuitive, and I feel like they don't necessarily rely on this concept of Riemann integration. So I'll give you another 5 minutes to do this. Just a little quick trivia fact. The reason I keep referring to it as the Riemann integration is because there's another form of integration called Lebesgue integration. But we don't learn that in IB. It's very sad. So yeah, 1 more minute. This could very well be in your syllabus. I'll show you how to do it like immediately, like just right after. And this is an AA, by the way. Yeah, Aryan's right. Okay, cool. So let me just continue, and I'll go ahead and solve the problem. I'm not actually sure if I can even like share this document with you guys at this stage, because like it has like pirate content, so not allowed for server sharing. And I definitely am not pirating this content. I just, I'm just a teacher. I have a question bank account. Just everyone just be quiet. Why did I take this part of the question? Oh, my whiteboard is messing up again. Perfect. Die. There, it's much better. Okay, so writing on a lower bound for 1 over n cubed. This one is super simple because that's why it's like only 1 mark actually. So the reason why that is because this is basically what's over here, and what you need to find is a lower bound for this. And a lower bound for this is just whatever this is, because that's like right below it. So the lower bound for this is whatever the value for this was, which was 1 over 32. That's why you would just write that down as the lower bound for the answer, and that's like your 1 mark right over there. Now, the upper bound for this can be solved for by utilizing the value of this. So you know that the sum of n equals to 5 as equal to infinity of 1 over n cubed is less than 1 over 32. That's for sure. And the reason you know that is because you know that it's less than that integral over there, and the integral's value is 1 over 32. And hence the entire thing must have value less than 1 over 32, and that's why you can like do this basically. And then what you can also notice is that when you're looking at n equals to this function, this is the same thing as saying the sum from going from n equals to 4 to infinity of 1 over n cubed minus 1 over 64, if that makes sense. So essentially what you're doing is that you're moving the n slightly forward 1. So you're basically moving it to n equals to 4. So you're adding another rectangle, but the value of that rectangle is 1 over 64. So in order to keep the equality correct, you need to basically take away 1 over 64 from that inequality. So this is the same thing as whatever this is, but now what you've done is that you've basically added more to the sigma, and you've taken away 1 over 64, and that's less than 1 over 32. And hence you can move the 1 over 64 to the other side, and you'll know that the sum of n equals to 4 to infinity is of 1 over n cubed is less than 1 over 32 plus 1 over 64, which is 3 over 64. And that's your upper bound, so it's an upper bound for it. And you have a lower bound, which is 1 over 32. And there you go. So now you know that's how you just like found the upper and lower bound for the function. That's 3 marks right over there to be able to do that and notice how to like manipulate this. Again, there's no real way for you to figure this out. Like you could have found some other lower bound or some other upper bound, but what they wanted you to do is use the facts and the information given in the question, because that's what you need to use. Like it would be really stupid because like sometimes you could like say the lower bound is like 0, because who cares anyway? It's like it's obviously like greater than 0, but you need to make sure to use the information they give you and to be able to utilize that instead. And yeah, that's how you solve that question. Pretty simple. Why is there a massive Lamau? Okay, so what is the marking scheme like? Oh, here, I'll pop in and show you the marking scheme. I think the marks might have used something slightly different, but here, so that's what I do. So C, lower bound is 1 over 30, you just get that one part, just A1, that's it. And there's also like, I think this is error carry forward, I think. This is a forward error from part A. So if you messed up part A and like messed up the integration, and you put exactly what the part A was, you'll get a mark for it anyways. Anyways, so the method one, so here, this is your first one, so like using, noting the first fact, and then basically the manipulation with 1 over 64 right over here, and then finally the upper bound, which is the answer. And again, if you make the same mistake in part C or part A or anything like that, you can always like, it'll carry forward. So this is the technique I used. The other technique that could be used is changing the inequality in a different way. So also this is another upper bound that you could create, and that's basically by utilizing the integral from 3 to infinity. So instead of it's basically like instead of like utilizing the previous information, you just like take like 1 over you know that this is lower, you know that this is smaller than whatever that integral is. So like, because notice that like this is n equals to 4, like the sum from n equals to 4, like with 1 over n cubed, and this is like the integral from 3 to infinity, and you know that it has to be lower, this has to be smaller than this. So you just evaluate this again, and you create a new upper bound that's like completely new. However, this is probably way longer. Like you still have to like integrate, like you have to like do more stuff. I think this is a lot easier. If you're like comfortable with the idea of sums and stuff, this is very simple. But if you like really like don't like that, and you just want to like compare it to some other integral you might know, you might as well just go along with method 2. Seems like examiners had nothing to say about this question at all, which is nice. Okay. Why is there a pin here? Oh, okay. Hop around. I'm not sure. Okay. Next question. Yeah, fundamental theorem of calculus. Again, the fundamental theorem of calculus basically says this, and it's very simple little function over here. If you have some function f of x, capital F of x, which is equal to the integral of f of t dt from 0 to x, then the f prime of x, which means the derivative of the capital F of x, is equal to f of x, right? So essentially what this is saying in very complicated terminology is that when you if a function is an integral of a function from 0 up to like some value x, then the derivative of that function is just the integrated function itself. And it's basically like, this is kind of like showing the fact that you can like cancel out like these integrals basically. So like you can like cancel out the fact that you're like integrating it and then differentiating it, and that basically gives you the exact same answer at the end, like f of x, like right over here, like you just get f of x. So just quickly being able to like use this, or like just try and solve this question. It might also require some chain rule stuff, so just try that as well. Another 5 minutes for that.
Okay, Andrew, fundamental theorem of calculus is like totally fine. Like, it's nothing compared to any of your questions. Okay, Riemann sums are also really pretty, okay? FTC, Riemann sums, they're like nice and beautiful. Like, cause they're like fundamental, you know? Yeah, essentially that's what it is. Yeah, that's basically what it is. I mean, in terms of like IB, that's all you need to know, really. Okay, cool. I'm gonna go ahead and answer the question. So I'll pop back in here, the canvas. Oh, copy pasted correctly for the first time and forever. No, it didn't copy paste correctly at all. That's the wrong question. Perfect. Okay. So the first part of the question, write down the derivative of f of x. And again, note that this is what you're doing when you're taking the derivative of f of x. You're doing d of dx of the integral from 0 to x of ln 2 plus sine t dt. And what this does is that basically what this says is that the integral cancels with the derivative essentially, and what you're left with is ln 2 plus sine x. It's very, very important that you don't leave it as ln of 2 plus sine t, because it is not ln 2 plus sine t. It is ln 2 plus sine x. So what happens when you integrate this? What you do is that you integrate it, then you have this x. You evaluate it with respect to the 0 and the x, and then it becomes in terms of the x, and then you differentiate that, and you end up back with the original thing, but it's all in terms of x's, because that's how this works. So you need to make ln. It's actually very important that you have ln of 2 plus sine x. The next part, by differentiating f of x squared, obtain an expression for the derivative of this with respect to x. And the way you would do this is this. So by differentiate, so if you were to differentiate f of x squared, what you would do is that you would get f x squared. We also need to multiply by the inside, so you get 2x in the front of it, right? So if you're gonna so the derivative of f of x squared is actually equal to the derivative of f of x squared times 2x. So what you would have to do for this situation is you want to find an expression for the derivative from 0 to x squared of ln 2 plus sine t dt. And the way you would do that is you would use the chain rule on it. So you do is you would get you know that d of dx of f of x squared is equal to 2x f derivative of x squared. So you know that this is equal to 2x, and we already know that the derivative of x is equal to ln 2 plus sine x. So we know it's ln of 2 plus sine, but not just x, because you have to put in the x squared now, of x squared, like so. And that. And that's what the final answer is. That's what it is with respect to x. And now finally, for the last part of the question, if you're trying to figure out an expression for the derivative of this whole thing, the way you would do it is that first of all, you need to figure out a way in order to actually split this up into stuff that you already know the answer to. And the way you can do that is to note that if you have any given function, and if you have a lower bound and an upper bound, it's the same thing as evaluating from 0 to the upper bound minus 0 for the lower bound. And the reason this works is, like, let's just quickly look at a curve, some curve, and you have some lower bound and you have some upper bound, and you want to find the area over here right in the middle of the upper bound and the lower bound. What you could do is that you could find the area of this entire portion over here. Then you can find the area that's from 0 to the upper bound, and you can find the area of the portion from 0 to the lower bound. Then take away the portion of this from portion, from the entire portion, to get this portion. So again, you do the exact same thing over here. You do the integral from 0 to x squared of ln 2 plus sine t dt. Minus the integral from 0 to x of ln 2 plus sine t dt. And that's what this integral is the same thing as. And then we can differentiate. So d of dx of this, d of dx of this. The d of dx of this we've already shown before is 2x ln 2 plus sine x squared. So we just showed that in part B. And minus the whatever this is, we've also shown that in part A, so that's just minus ln 2 plus sine x, and that's your expression for the derivative. So that's how that works, and that's perfect. So if you have any questions about that, you can ask. So negative ln 2 also, right? Leibniz rule first. I don't know. I haven't used Leibniz rule. Like, I just do stuff. And this is how it works. For A, negative ln 2. For A. No, it's not a negative ln 2 for A. It's just ln of L, because from 0 to x. Oh yeah. So it is negative. So that's why I put the negative in over here. So it's negative of ln 2 plus sine x. Because that's why I put a negative over here. From 0 to x. So yeah. So from 0 to x, it's negative. You have to take that away, so it's negative ln 2 plus sine x, and that's what I put in the final answer. Does that make sense? Oh my god. Why would you want to use this? It just looks like notation at this stage. Yeah, fair enough. This is like the exact same thing. Yeah, this just looks like bad, like horrible, crazy notation. It's exactly the same thing I just did, but like intuitively speaking. Yeah, it is the same. It's exactly the same. Okay. I'm going to continue. We don't need to discuss Leibniz rule anymore. It's fine. Okay, so I'm just going to skip over differential equations. Let's just teach Rolle's theorem and mean value theorem for a second, and then I'll pop over back to differential equations. Oh, I also just have to like show you what Taylor series are, you know, boring stuff. Series for differential equations. Okay. The D's are italicized? Oh yeah, they didn't use math term. Oh my god, disgusting. Um, Rolle's theorem. If f is equal to b, then it exists on a is b. Okay. Rolle's theorem seems to me to be very intuitive, and it should just like plop into place, like really, because this is what it is. It says basically that if you have some curve, right, some weird curve, right, and you have some value of a, and you have some value over here of b, it says that if f of a is equal to f of b in the interval from a to b, so in the interval from a to b, there exists some f of c such that it is equal to 0. There's some like f prime of c such that it's equal to 0. Now what does this mean? It basically says that if you have 2 points on a curve which have the same y value, which means that they're the same height, and they're equal to each other, that means that between these 2 points there exists some other point which has derivative equal to 0, which means that it's flat. And note that just looking at this curve, it's obvious that it's true. Like if you have a over here and b over here, you know that over here, you can notice that right over here there's a 0, right over here there's a 0, and like that's like, and again this kind of makes sense. Like if you have like 2 values that are like a and b that are like it's like if the curve is like going up for a little bit, eventually it has to come down again in order to like go back to the b. If it's going down a bit, it has to go up again for the b, and if it goes up and down or up, that automatically gives it a maximum. If it's not going up or down, it's just going as a straight line, which means that obviously every single point in this interval has a value c, has a value of 0 for the derivative. So yeah, that's like, this is what the Rolle's theorem is. However, a little more general version of the Rolle's theorem is the mean value theorem. So you can like extend this idea to any possible slope, not just 0. So if you have, oh, why did it go to blue? Fascinating concept. If you have some curve like that, you have some value over here at a, you have some value over here at b, and you need, so based on this, now what the mean value theorem says is that for a and b, right, there exists some point inside over here that has the same slope that if you that has the same slope as if you just connected these 2 points and created a line between them. So if you like looked at the slope just between these 2 points, so if you made it like f of b minus f of a, right, using the slope definition, y minus like delta y over delta x, so like f of b minus f of a over b minus a, right? So say we got some slope, and say that slope is m, right? So some point over here on this curve in between these 2 points also has that exact same slope m. So the derivative of the curve at one of these points is also equal to that slope m. Now again, this should make sense, right? Because if you're going all the way from here all the way up to here, at some point you need to be able, like if you're like going like this and then coming back up, at some point you're going to have like this slope, right? So as you notice, like there's that slope over here, maybe there's that slope over here, there's that slope over here, like that's basically what that means, right? Another very interesting thing to just quickly mention is that another way to prove that this is true is by using Rolle's theorem. Because if you remember what Rolle's theorem is like, okay, first of all, Rolle's theorem is just this theorem, just like as with like a simplified like version, like only one like scenario. If you use like Rolle's theorem, right, and you looked at this, and you looked at that, and you looked at that right there, right, and you notice that there's a 0 here, there's a 0 here, and in between a and b there must be at least some 0 for some scenario. What you could do is you could just rotate this curve. So like you can just like, you can rotate any curve in order to make sure that like, as long as you can like rotate the curve in any orientation you want to rotate it in, like you could end up with a mean value theorem. Like if you rotated this curve, and you could make the curve look like this now. And now the new values of a and b are like over here, and like these are the 2 points, and that's like the slope between them. You know that this slope works and this slope works. So essentially what it looks like is like a rotation. So like the Rolle theorem, the mean value theorem are really the same theorem.
but they're like rotations of each other essentially, like for whatever arbitrary slope you want to find between 2 points. And I feel like, yeah, this is a slightly intuitive concept. So let me see. Yeah, provided it's all, what is this? Provided it's all continuous. Yeah, I guess so. I'm not sure what that's referring to, but yeah. Provided like the entire like domain that you're like looking over is continuous, of course, yeah. And that's what mean and like that role theorem is and mean value theorem is, and that's basically that, right? Yeah. So the next topic. So I just done with that. If anyone has questions about that, you can ask. But I think it's one of the simpler topics. Like differential equation probably way harder. And yeah, okay. So next question: Taylor series, Maclaurin series. This is a fun topic because again I'm gonna like wait. Let me just actually open up the data booklet because it's in the data booklet. I don't even want to really go over this if it's in the data booklet, and like at the end of the day for the exam you can just use the data booklet. But also strictly speaking, I'm not a very good. I don't explain this concept very well. Like the Taylor series, Maclaurin series concept, I don't explain very well. But there is a dude who does explain very well. It's 3B1B. So I'm gonna pop a link of this. It's not related to it's not related to like the stuff I'm gonna talk about later. So you can watch this later if you like. I'm gonna plop it up over here. This is a very useful video series for learning the Taylor series, Maclaurin series, and what they mean. And after you know what that means, you're gonna look at the data booklet and you'll see that it's basically exactly what's in the data booklet. And I'm just gonna pop over in the data booklet and show you what that looks like. Okay, here. So, this is what Taylor series looks like, right over here. That's what the Taylor series looks like, and that's what the Maclaurin series looks like. So basically what the Taylor series and the Maclaurin series do is that they create a polynomial which looks exactly like any given function. So for example, you have some really weird looking function like e to the power of sine x or something. Like that's a weird function. You can't really differentiate it very easily. You can't really work with it very easily. You can't really do many things with it. So you might want to make it into a polynomial, right? Because polynomials are easy to differentiate. They're easy to integrate. They're just generally useful, right? So what you do is basically you evaluate that function at 0, right? And you make that your first term. Then you add to that function evaluated at 0, the derivative of that function evaluated at 0 times x. Then x squared over 2 factorial times that function's second derivative evaluated at 0, and so on. Like 2 factorial, then 3 factorial, then 4 factorial, it'll keep going forever. And that's what the Maclaurin series is. And basically what it does, it creates a polynomial that looks exactly like the original function, but like around 0, basically. So this is a pretty like useful thing to use. And and you can just refer to the data booklet to see how to do it every single time, basically. And the next thing is the Taylor series. So the Taylor series is basically looking at if you want to make sure that you do it not just at 0, like you can do it at a or b or like it's any other interval. So like 1, 2, 3, like you want to center it at any other point. If you want to center it at another point, you need to use the Taylor series definition, which is basically the same thing. So instead of evaluating at 0, you evaluate at a, and you make sure that every x is being adjusted by some constant like x minus a or something of the sort. And yeah, so that's what that looks like. There's also like this remainder over here. So like sometimes questions will ask you like what the remainder is. So sometimes like what you end up having is that you'll end up having like some polynomial, and like the polynomial obviously doesn't like exactly like match the original function. So you have like some remainder like that like makes it work basically. So like there's a Lagrange form for the remainder right over here. So this is what it looks like. This is literally just like a random like. This is just a formula, and like they'll give you all the values you need for like, entering into this formula. It's quite simple, and that's what the remainder is. There's many like different Maclaurin series for some special functions like e to the x, ln 1 plus x, sine x, cosine x, arctan x.
And basically, you can also manipulate these like however you like. So, for example, if you had like e to the x, right, you can manipulate that and make it like e to the power of negative x, and like you can just like replace all the x's in the Maclaurin series expansion with negative x's, and it would all work out perfectly. And if you want to like make it e to the x plus e to the negative x, you can just like replace all of them with negative x's and then like add the two series. So if you had like sine x times cosine x, you can just like multiply the two series together and then like evaluate some terms or something. Like it's very flexible. You can use these polynomials however you like, move them around, shift them around, like multiply them, add them together, change what the x's are inside of them. Like you can do all kinds of things. It's very fun. So yeah, the type of Taylor series, Maclaurin series. If you want to like get like a more like conceptual understanding, please watch the video series. It's a lot better than anything I could ever explain. And obviously it's like animations and cool looking stuff. So now we're looking at differential equations. So differential equations are basically where you have derivatives and differentials inside of your function. So like you have these things that look very you need to be able to solve for what the derivatives are at different points of different functions, and like you use differential equations for that. So the most simple differential equations are first order differential equations, which look like this. They are of this form. So you have some dy dx, which is equal to some f of x over g of y. And basically what this says is that the derivative of y with respect to x is equal to some function of x over some function of y. And the reason why this is so simple to solve is because you can just move this g of y to the other side. So you can multiply both sides by g of y. Then you can also multiply both sides by dx. So if you multiply both sides by gy, you get the g of y in front over there with the dy. If you multiply both sides by dx, you'll get f of x dx. And notice that's g of y times some infinitesimal dy, and that's f of x times some infinitesimal dx. What you can do is that you can plop an integral sign right in front of it, from an integral sign in front of both of them, then just integrate g of y with respect to y, and then integrate f of x with respect to x. So this is like super simple and super fun because like it's separable. So you're able to separate all the x's on one side and all the y's on one side, and then just be able to solve the integral through this technique. And this is why they're like simple first order differential equations, and they're very like they just use like simple separation, and they're very separable. It's like super cool, super nice, super sweet. And one little thing that might plop up at any given point is slope fields and isoclines. So 1 second, I'm gonna look at the 1 second. Wait a second. Wait a minute. I'll come back to this. Let's do Euler's method of computation in a second. I think I'll do slope fields last. I think that makes more sense. Okay, let's do Euler's method of computation. What the hell? So Euler's method of computation is basically a way to solve a differential equation when when it's not easily separable or something, and you just want to like try and figure out exactly how to like solve the equation. And the way you do it is by using the data booklet. So I'm just gonna I'll just outline what the Marx scheme is saying essentially, and it'll make a lot more sense that way. So over here, basically what's happening is that you're given some. Oh no, that's not what I wanted to do. So dy dx minus 2y squared is equal to e to the x. So this is giving some relationship basically. So what it's doing is it's telling you that this is how you can solve for the differential at any given point by just plugging in for y and plugging in for x. So when y is equal to 1, y equals to 1 when x is equal to 0. So that's another like piece of information they're giving you for this function. So what they're asking you is to find, using Euler's method, which is basically like a computational technique, with step length of 0.1, to find an approximation for the value of y when x is equal to 0.4. So the way that we would do this is that let's just look at what this actually means. So like we're looking at some function and it has some curve, and basically what we're doing is that we know that this is a value of that curve. One sec, I don't know why I made that so thick. What the hell? This is some function. This is some point, and we know that that point occurs at like some x. And then what we want to do is we want to use the differential, like use the derivative to like slope it until this point, and then slope it again till that point, and then like slope it, like keep like using the slope to slowly edge forward to the next value essentially. So that's basically what we're doing over here. So what we're doing is that you start with some value 1, right? And so you start with x equal to 0. So you start with x equals to 0, which is right over here, and you have y equals to 1. The value of dy dx when you plug in x equals to 0 and y equals to 1 is 3. And then that's why you know that if you're using some step length of 0.1, that 3, which is the slope, is going to be continued to be used for a length of 0.1. So you have some slope 3, which is being, if you were to like continue along that slope for 1 unit length, you would go up by 3. But if you were to continue only by 0.1 unit length, so 0.1 unit length, you would go up by 0.3. So that's what they mean by like why they made 3 to 0.3. And so 0.1 is associated with 0.3. They could have a different step length, for example. They could have a step length of 0.2, in which case you need to multiply 0.2 times whatever the slope is at that point. Then what you do is that now you know that the change in y is going to be 0.3 when you're going from 0 to 0.1, because the slope at that point is going from 0 to 0.1. This is an approximation technique, obviously, because like even across the slope length of 0.1, there might be more changes in the derivative. But we're assuming that for that 0.1, the change is approximately and roughly the same. So that's why you can just continue going along that path. So you can go 0.1. So if you go along x 0.1, then like following that exact same slope at 0, you get 1.3. And then when you calculate for dy dx, you get 4.4, like this really long number. And then when you're calculating the slope, what the change in y is going to be once you carry along that slope for a length of 0.1, you get this number. Then you add that number to the y again. And you keep doing this again and again until you get a value for x equal to 0.4 and whatever the corresponding y value is. And that's what the approximation is going to give you. And then you just need to like show that that's what the approximation is. Note, I think that this method is actually shown it's shown here as well. So if you like magically one day like forget what this is, I think it's right over here. Yeah, so it's right over here. So xn plus 1 is equal to the previous x plus h, which is whatever your like constant step length is. And then yn plus 1 is equal to yn, which is whatever the previous yn is, plus h, which is the step length, times the derivative, basically, like whatever your function is, and however your function is changed. You need to make sure that you also are very accurate with your numbers in this. So that seems to be like an important thing that like they miss out. So your approximation needs to approximate to 3.85, and you won't get the marks if you don't do that. You need to make sure that you have like all your approximations down to like all the decimal places, and you don't mess them up or anything like that. So yeah, let's keep going. Homogeneous differential equations. Now, the thing with homogeneous differential equations is that they're in this form essentially. So I'm just gonna pop up and show you what form that is. Wait, I have forgotten what form it is. 1 second. Okay, yeah, I remember what the form is. It basically looks like this. You have some function of x and y. So basically what I mean by f(x, y) is that you have some function which is dependent on both x and y. So like it has x's and y's in it. And that is being multiplied by dy. And that's equal to some function, some other function, I'm going to call that function g, of xy, dx. So again, g is another function with some x's and y's. It could be anything. It could be like x squared plus y or x plus y squared or something like that. It could be anything. And this is what a homogeneous differential equation is. Now, usually this is very difficult to solve for because note that it's not separable, right? Like, because if you like put an integral, popped an integral here and popped an integral over here, like you're integrating something that has x's and y's in it with respect to y, and like it doesn't work very well over here. And like over here, you're integrating something with x's and y's in it, and like you integrate with respect to x, and like it doesn't work very well. Like you can't exactly integrate that. Like how are you meant to integrate this? Like it's like you can't just treat y as a constant if you're integrating with respect to x because y is dependent on x. So what do you do in this situation? Now it turns out that the best way to solve for solve for problems like these is to use something called use a substitute for y. So you use like a substitution for y. So instead of like thinking of y as y, you think of y as some function of x. So you think of y as equal to vx, right? So v is some function of x times x, and that's what y is equal to. And essentially what that allows you to do, it allows you to actually make it separable. So let's think about what exactly is happening over here. So if you have y is equal to vx, and what you end up doing is that you actually replace all the y's in the function in the question with vx's. And then you also have to replace all the dy dx's in the function with whatever with d of dx of vx, right? And note that the derivative of vx with respect to x is v plus dv dx x. The reason why we use the chain rule over here is because v is some function of x is some function of x, obviously, because it's x. So you need to use the chain rule. So what I did was over here is I left v alone and I differentiated x and got 1, so it just disappeared. And then x I differentiated, v and got dv dx, and then had an x add, I had to keep the x hadn't differentiated, so I just plopped it up in the front. And this is what I did. Now if you use these two substitutions, your function will become separable. That's just like the special property of how this works. It'll become separable. You'll be able to use you'll be able to find something in terms of v and x's, and then what you'll be able to do is then you can use the fact that v is equal to y over x to solve for the actual homogeneous differential equation. Snip in the Q in the mark scheme. Which one was this? I'll just pop that in there. Sorry. So I'm gonna look at the next question over here. That's for the marks here. So just try and solve this question, and I'll give you maybe, let me see how many marks this is. Why is it not telling me how many marks this is? 11 marks. So I'll give you guys around maybe 10 minutes. Okay, cool. I'm gonna explain now. So hopefully you guys are listening. Wow, we have way fewer people. That's amazing. Um, let's just open and solve the questions. So, hopefully this works. Nope, it didn't work. I need to reload this page again. What an absolute need. Okay, here we go. So, okay, so given the y is negative 1, given the form y equals to f of x. So the way that we would solve for this one is we need to again use the fact that y equals to vx and that dy dx is equal to v plus dv dx x. And so let's plug everything in. So x squared and dy dx, so that's x squared times v plus dv dx x is equal to y squared, which is equal now to v squared x squared plus 3xy, which is now equal to vx times x times 3, so that's 3 vx squared plus 2x squared. Note one really cool thing that just happened. X squared times v plus dv dx x is equal to x squared times v squared plus 3v plus 2. Our x squared just canceled out. This x squared over here cancels out with this x squared over here, which is super convenient. And now, again, we can solve. So I'm going to try and isolate this dv dx on one side. So I'm going to make it a dv dx. I'm going to like solve now. So dv dx times x is equal to v squared plus 3v minus v, because I'm taking the v all to the other side. So I'm going to make it a v squared plus 2v plus 2. And that's what dv dx x is. Then the next thing I'm going to do is I'm just going to... Wait, am I sure that that's 2? 1 second. Okay, cool. Now what I'm going to do is I'm going to make the dx on one side and the dv's on one side, all the v stuff. So the v stuff is on one side, so I'm going to make that 1 over v squared plus 2v plus 2 dv, and that's equal to 1 over x dx. So the dx goes to that side, 1 over x goes to that side, and it's just the integral of these two things. This is a slightly difficult integral because the one on the right is obviously quite easy, because we know that this integral can just be expressed at the integral of 1 over x is just ln of x, right, plus c. So we know that that works out fine. However, the other integral is not as simple. And just give me 1 minute. Yeah, so the other integral, you need to be able to reorganize it in a different way, and then use the data booklet to be able to like figure out what the integral actually looks like. And it is slightly difficult. So let's just reorganize this one. So what it ends up looking like is this. So it's actually the integral of 1 over v plus 1 squared plus 1, right, dv, which, if you recall, is equal to arctan of v plus 1. So that, if you go back to your the data booklet, you'll see this is arctan is equal arctan of v plus 1 is this thing can be like, is this the integral of this is arctan. So whenever you have stuff like this, you can try and if you can try and make it into a perfect squared plus some number, you can probably put it into an arctan. So this is what the arctan looks like. So the arctan of v plus 1 is equal to ln of x plus c. And now we can substitute back in for v. So we know that y is equal to vx, so we know that v is equal to y over x. So this is the same thing as arctan of y over what? I'm messy man. Arctan of y over x plus 1 is equal to ln of x plus c. And then when x is equal to 1 and y is equal to -1, The x, so it knows, you know that when y is equal to -1, x equal to 1, so you can like just plug those in as well, so you can like to try and find out what the value of c is. So arctan of y is equal to -1 over x when x is equal to 1, so it's equal to -1 plus 1, that's arctan of 0, which is equal to ln of x, and x is equal to 1 again, so equal to ln of 1 plus c. And note that ln of 1 is 0, and arctan of 0 is also equal to 0, so hence c is equal to 0. So you know that your function is equal to ln of x, which is equal to arctan of y over x plus 1. That's what your function looks like. And if you wanted to like, that's what your function looks like. However, you do need to like, you need to make it into a form that's in terms of y. So again, you would do this by looking changing up this arctan thing over here. So basically, flip the arctan to the other side. So y over x plus 1 is equal to the tangent of ln of x. The tangent of ln of x. So y is equal to the tangent of ln of x minus 1 times x. So tangent of ln of x minus 1 times x, like so. So that's what that looks like. And that's the homogeneous differentiation. So I think the hardest part of this question really is not, the homogeneous thing will always work, as long as like, as long as none of the other differential techniques are working, use this one. Or if you notice like the form that I told you before, like it's like, it looks like there's like some like stuff and like some stuff and like they just like multiply into each other. Again, this is the way to solve it, and the technique is quite like simple and like it'll always work. The only hard part is the integral, like the integral part over here where I had to like solve the integrals. That's the difficult part. Because like solving the integral of 1 over v squared plus 2v plus 2, that's hard. And you need to recognize that you can make that into an arctan part, and that's really the hardest part of this question. Regardless, this is an 11 mark question, so you'll comfortably have about like maybe 15 to 16 minutes to solve this question. That's quite a long time. So tan theta is equal to v plus 1 sub. I can use data book as a simplifying the cosine for. Oh, that's very sad. Yeah, that's very long. But yeah, this is what, in the data booklet they have that, so for the integral. Yeah, if stuff is like really not working out and like everything's like falling apart, like go back to your data booklet and read every single integral there, because it's probably one of them, and you probably just like aren't remembering. Final differential equation technique, before I go back to like slopes and isoclimes real quick, I'm just going to look at the integrating factor and see what that, let's explain what that is. Again, there's a really good video behind how the integrating factor works, so I'm going to like link that, but I'm also going to go over it really quickly over here. So here, this one works out. Here, so black pen, red pen's video is really good, so I'm going to pop that in here for the integrating factor. So if you want to watch this later, that's fine. But I'm going to quickly go over the concept behind the integrating factor and what it does. And basically what it says is this. It says that it is the form, it's of the form, dy dx plus some function p of x times y is equal to some other function f of x on the other side. Right, so let me just quickly check whether that's true. And yeah, that's just what it is. I see benzene is typing something, so I'm gonna go look at what that is. Yeah, black pen, red pen. Yeah. Is that benzene? No, that, I don't know what this is. Okay, whatever. Dy dx plus p of x 1 y is equal to f of x. Basically, the idea behind the integrating factor is that you're trying to basically use the chain rule. So say I had some random function, y times g of x, right? And y is some like y is some function of x as well, and I have some g of x, so that's another function of x as well. So actually, to make this very clear, that's actually no, it's fine. Y times g of x, right? That's fine. Let's try and differentiate this. When you differentiate this, you differentiate the y term, and you get dy dx times g of x, right? And then when you integrate when you differentiate the g of x term, when you add, you differentiate the g of x term, you get some other function. You get some g prime of x, right? And you get and then you get the y. You just have a y over there, right? This is your form, correct? And what the integrating factor is really trying to do is that the integrating factor technique, really what it's trying to do is trying to get this form, getting this form into this form, and then what that lets you do is go from here back to here. So what you do is you try and find some function. So you can multiply this entire thing by that function, multiply all of this by that function, and then what that does is it allows you to have some dy dx times some function plus that function's derivative times y. So what you want to do is you want to multiply p of x by some function such that it becomes the derivative of that function. And the way that we do this is by using the integrating factor, which you use a formula for basically, or you can just try and identify that that's the case, but usually the formula is quite simple and you can just use the formula for figuring out what the integrating factor is. However, note that what it's really trying to do is trying to multiply p of x by some function such that p of x becomes such that product becomes the derivative of the original function itself. So let's just think about what that means again. So what you're doing is that you're trying to find some function f of x such that when you multiply that by p of x, that is equal to f prime of x itself. Right? So that's what that looks like. So in other words, what that looks like is you have some y times p of x, which is equal to some dy dx. I'm not going to go into the details of this, but there's there's a solution to this, this kind of differential equation, which just isn't covered in IB. But basically, the solution to this kind of differential equation is e to the power of the integral of p of x, which is very cool. P of x dx, which is very cool because this pops up in so the integrating factor, which is what you wanted to find out. You wanted to find out this integrating factor f of x. So f of x is actually equal to this. So the way that we would look at that is if you look over here, the integrating factor over here for this function, the integrating factor is e to the power of the integral of p of x dx, and it's basically by solving this differential equation that you're able to get this power. So I'm just gonna so what that essentially entails is that after you do that, you're meant to multiply the entire function by it. So that means that whatever the integrating factor is, you multiply this by it, 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 and then you'll end up with some form, right, which looks like this. Then you need to go backwards and go back to this form, and then use this form is equal to f of x times some function, and then solve that way, which will then be separable, hopefully. So the way that you would do that is to go back to, and I'm just going to give an example right now. So here's so you can try and solve this again. They're giving you when y is equal to 1 and x equal to 0 because that's a constant. So again, I'm going to just show you this right over here. So give your answer in the form y equals to f of x. Yes. Okay, I'll give you 5 minutes for that. And this is our second last thing, so it'll be pretty done after this. Okay, alright, that's cool. We'll check if the answer's correct soon, because I'll be solving it as well. I don't think that's correct. But probably close, I think. Yeah, I don't think the X is first order in the top, but that's okay. I'll go through the solution right now. I'll go through the solution right now. Right here. Okay, so here's what I do. First of all, we need to make this actually into the form where we can use the integrating factor, because right now the dy dx will be multiplied by something, but that's not what we want. We want the dy dx to not be multiplied by something. So the way we do that is we divide everything by x minus 1. So we get dy dx is equal to x over x minus 1
times y, and x minus 1 divided by x minus 1 is just 1, so it's e to the negative x. Oh wait, why did I put an equal sign there? You know, I'm really an idiot. So now, what do we do? So now we figured out that our p of x is equal to x over x minus 1. Right over here. It's right over here. And that's our general form. Note that you can even check this. If you forget this general form, you can always pop into your data booklet, and it's literally right over here. If you have like some derivative y prime plus p of x times y is equal to q of x, the integrating factor is e to the power of integral of p of x dx. Yeah, that's what that looks like. Pretty cool. So p of x is equal to x over x minus 1. First, just to try and figure out what the integral of this is. So this could be slightly difficult sometimes, like because finding the integral of x over x minus 1 doesn't feel as obvious at first. But after a second, it makes sense. Because you can rewrite this as x minus 1 plus 1, right, over x minus 1. Which, if you notice, you can like split the numerator, and you'll get x minus 1 over x minus 1, plus 1 over x minus 1, and you get that integral, right? So this cancels out, and it's just so this is just 1, so that's just 1 plus 1 over x minus 1 dx. So that what that ends up giving you is just x plus ln of x minus 1, right? So because 1 over x minus 1, the derivative is just ln of x minus 1, and then the x minus 1 and x plus 1 gives you 1, so the integral of 1 is just x plus ln x. So the integral is x plus ln x minus 1. So the integrating factor is e to the power of that integral. So it's e to the power of x plus ln x minus 1. That's what you need to multiply everything by. But notice, this is, when you take this is the same as saying e to the x times e to the ln of x minus 1. So e to the ln of anything is just what that anything is. So it's just equal to x minus 1 times e to the x. And that's what our integrating factor is, and that's what we need to multiply everything in the equation by. So let's go ahead and do that. So we first multiply the first part, so that's x minus 1 e to the x dy dx, right? Plus, so then we get x over x minus 1 times y times our integrating factor. So then we also know that actually simplifies into x e to the xy. So you'll notice that simplifies into that. And then the final portion right over here, the final end portion, e to the negative x. E to the negative x times x minus y to e to the x. The e to the x and the e to the negative x will cancel out, and it'll just leave you with x minus 1. So this is what your function looks like. And now note that what's really, really cool about this is that the derivative of 1 minute. I'm just getting a poop seat. 1 second. So if you have an original function, which is x e to the x minus e to the x, the derivative of this is actually equal to x e to the x, which is exactly what we wanted. We found some function that when you multiply it through, we multiplied by it, and we got some derivative, and this is what the original function looks like. And when you differentiate it, you get this function. And that's exactly what we wanted. So it's perfect. And what we can end up doing is we can now just rewrite this as d of dx of x minus 1 times e to the x times y. And note that if you were to actually differentiate this and take x minus 1 e to the x over here, so you have x minus 1 e to the x over here, and you differentiate the y, you get dy dx, plus you differentiate all of this, you get x e to the x, and then you multiply it just by y, and you get exactly what you wanted, and that's equal to x minus 1. Now this is a much, much easier integral to solve, especially if you just quickly take the integral, if you just take the integral of both sides, so this is what ends up happening. So say you can move the dx to the other side first of all. So you can take this is now what this simplifies is into d times x minus 1 e to the xy, which is equal to x minus 1 dx. So we put the integral in front of both of them. Now this is kind of confusing right over here. It could be slightly confusing. What it basically means is that you're taking the integral of nothing with respect to x minus 1 e to the xy. So when you're taking the integral of nothing, which is 1 basically,
with respect to anything, it's just that what that variable is. So what this whole thing just equals to x minus 1 times e to the x y. And the other side, which is the integral of x minus 1 dx, is just equal to x squared minus x plus c. So x squared over 2 minus x plus c. And then by subbing in for x and y, because we know that our x and y values, x value is equal to x is equal to 0 and y is equal to 1 from the original question, we can if you can plug everything in, you'll find that c is equal to -1, but I'm not going to go ahead and do all of that work. And then finally, when you plug in for a value of c, you can solve for y, and you'll be able to solve for y, and you'll see that y is actually equal to x squared minus 2x minus 2 over 2 times x minus 1 e to the x. I can show you what that looks like by just I can show you what the entire process is in the marks game, but basically that's how you solve using the integrating factor. But we do cover y sine t, x equal to cosine t substitution in IB. I'm learning stuff from different books, so I tend to mix it up. Yes, this is one more thing that you learn in IB. Basically, what you have to do in this scenario is that you just like that stuff's already in the core, like trig substitutions. So that's fine. But oh wait, you're talking about parametrics. Oh, okay. So y equals sine t and x equals, that's the parametric form. We don't talk about parametric form in IB at all. That's AP. So yeah, there's no parametric form. Oh, okay, you rushed everything wrong. Okay, cool. Okay, cool. Let me just send you the marks game for that. That's 13 marks. So it's like you could easily spend like 20 minutes on this question. Like it's intense. But the real thing is that you shouldn't be spending 20 minutes on this question, because you should be able to get it much faster, because you should know how to do it. Okay, so that's it. And the last thing for today is slope fields and isoclines, which is a kind of a weird concept to me as well. Like the IB goes into it to some extent, but like they go so like shallowly into the integrating factor. Like it's like basically like, why would you even do it like at this stage? Like into the slope fields and isoclines, like why would you even try and do this at this stage? Basically what isoclines are is that usually when you have like derivatives like in like higher level, like in like very high levels, you would like represent the derivative as some function f of x. So like we have some function f of x. Oh wait 1 second. Like if you have some derivative dy dx, you're gonna represent dy dx as like f of xy, right? So like some function of x and y. And usually this is like fine. Like it's okay to just like this is fine, right? So what ends up happening is that you actually have like, because you have like some function f x y, what you're actually looking at is that every single point on this plane, right, has like some given like value, right, which is some slope basically. So what you can end up doing is that you can plug in some value of x and y. So say you want to look at like 1 1, so like x equal to 1, y is equal to 1, right over here, right? And then you could like solve for that and you'll find a slope. And then say that slope is like 2, so we know it looks like that. And so we can like draw and represent that point as a slope, and then you can like do that for every single point over here, and like you can get all different kinds of points. So you can actually like draw the slopes everywhere, and you end up with something called a slope field. So it's like a field of all the different slopes you can possibly have, and that's what the slope field is. It's kind of a weird concept. Like it doesn't really like mean like, yeah, it basically is just like a field of slopes, and like all have the same slope. But another very interesting thing that they can do is that you'll have something called isoclines. So an isocline is basically a line where along that line there is the exact same slope along that line. Now this line doesn't necessarily need to be straight in all contexts, but usually in IB context it is straight. And basically what the isocline says is that along this entire point, along this entire line, all the slopes are the same. So we notice like when we have like slope fields, there are all these different kinds of slopes everywhere. So it's just a line that through along that line, all the slopes are the same. So for example, if we let's just go straight into our our example over here. So I'm not gonna like ask you guys to do this because I don't think you'll be able to do it like just straight up. But here's what it looks like. So dy dx is equal to f of xy, where f of xy is equal to y minus 2x. So what ends up happening is that the first question is sketch on one diagram the 4 isoclines corresponding to f of xy is equal to k, where k takes the values negative 1, negative 0.5, 0, and 1. Indicate clearly where each isocline crosses the y-axis. Basically what this means to say, it means to say that at, we want to find out, draw a line, which along that line, the slope is always equal to whatever k is. So k is negative 1, negative 0.5, 0, and 1. So you need to draw 4 lines. And you need to draw 4 of those isoclines. And this is what this basically does, basically. And the way that they find these 4 lines is by doing this. So let me just start focusing the snip. You take y minus 2x. So you take y minus 2x, and you set it equal to negative 1, right, which is one of the isoclines. And that equal, then you get y is equal to 2x minus 1. That's one of your lines. Then the other lines are just y is equal to 2x minus 1, 2x minus 0.5, 2x minus 0, 2x plus 2. Oh wait, 1 second. This is correct. Yeah. So y is equal to 2x minus 1, y is equal to 2x minus 0.5, y is equal to 2x, y is equal to 2x plus 1. So those are all the different like isoclines you can come up with. And by basically finding out all those isoclines, you can like draw them on like a graph. So first you would draw all the isoclines on the graph like without this curve. So just draw the isoclines. And that's basically what it is. And you should just show like it crosses at 1, negative 0.5, negative 1, and so on, right? And 0. So a curve C passes through the point 0, 1 and satisfies the differential equation above. Sketch C in your diagram. Now the way that you would do this is basically by knowing that curve C satisfies the differential equation, which means that it must satisfy those slope things that we just gave. So at different given points, it must have the slopes given by that differential equation. So sketch C on your diagram. Basically what that means, it passes through point 0, 1. So it's some curve, right, whose slope at this point right over here is 1, because that's that isocline over here, whose slope on this isocline is 0, whose slope on this isocline is negative 0.5, and whose slope on this isocline is negative 1. So you need to just like find a curve that looks like this basically, which has a maximum at like this on this isocline. But it could be like shaped anywhere. Like it could be shaped over here, it could be shaped over here, it could be shaped over here, or anywhere you want it to be. But basically what you end up doing is that you want it to be 0, 1, right? So you want it to pass through this point over here. And that's why the curve passes through specifically that point over there. The next are quite simple. They're just like, there's some other related things, which are other, like just going back to the other topic. So that's it. So yeah, that's the end of the session. So end of everything that I went through. That's everything that needed to go over. So that's it. Thank you for coming.